In this video, I'm going to start talking about alkynes, which are hydrocarbon chains that have triple bonds in them. So we saw in previous videos, we looked at the alkenes, which had a double bond, and so that was between the p orbitals on two adjacent carbons. So an alkyne means that we have these pi bonds formed from the p orbitals so two p orbitals from two adjacent carbons. And so these will have a single sigma bond and then two pi bonds. And so just like with the alkenes, these pi bonds are going to be able to be involved in a lot of different reactions. And actually quite a few of them are more or less the same types of reactions that we saw with the alkenes. So I'm not going to be spending as much time on the alkynes as I did on the alkenes. So it'll probably just be this video and the next video. And so as usual, the first thing to get out of the way with here is our nomenclature. And so just like when you have an alkane, then the two carbons would be an ethane. When you have an alkene, the two carbons would be an ethene. When you have two carbons here, you have ethyne. So we're just putting this Y in here when we are using the triple bonds when we're talking about these alkynes. And so the ethyne here has the common name acetylene, which you might be familiar with if you know anything about like welding. But then we can have the propyne, so this is three carbons, so that's where that pro prefix comes from. And again, we add that Y in there, so propyne. And the common name for this is methyl acetylene. So it looks like an acetylene right here, but then we just put this methyl group on it, so methyl acetylene. Then we can have two butyne here, and so this is our second carbon, and so in this four carbon chain, and so we put the two there to tell us that the triple bond is starting on that second carbon. And so we can look at something a little bit more substantial here. So this is 6-bromo-2-methyl-hept-3-ine. And so this has seven carbons in the main chain. And so the triple bond is closer over to this side. And so this is the carbon that we actually start counting from. And so that's why the bromine here is on the sixth carbon, and this methyl here is on the second carbon. Then this triple bond starts at the third carbon. So we have the hept-3-ine, or you might actually see it sometimes as methyl 3-heptyne, but this is often also used here. So that's just telling us that that triple bond starts on our third carbon. Again, I have two butyne here. That's just the same as this one above. Then we also have this 2-methyl-1-pentene-3-ine. And so this has a methyl group on the second carbon there. So the double bond here is closer over to this first carbon here. So we start counting from this carbon here. So that's the 1-pent right there, or this 1-pentene. So this starts, this ene here, this alkene, this double bond starts on the first carbon, so we call it 1-pentene. Then this is on the third carbon, so we have 3-ine there. And so that's an alkyne, meaning that we have both double and triple bonds in it. Then this one here, we have three. This should be butyne 2-ol, so there should be a T. There should be a T in right there. So that should have a T in right there. So it should be 3-butyne 2-ol. And so we're saying that this right here, this alcohol, this hydroxyl group is on our second carbon, and then this triple bond starts on the third carbon. So it's 3-butyne, and then the 2-ol here is for that hydroxyl group. Then down here we have this ether group on here. So this is the 4-methoxy. So this is a methoxy group right here. And so this has two, or the triple bond starts on the second carbon here. So it's 4-methoxy 2-hexyne, or you might see it as 4-methoxy hex 2-ine. Those are both correct ways of naming that. And so we see that this triple bond is sort of taking priority over this this methoxy group right here. And so we start counting from this carbon right here. And so the last thing here in the nomenclature is just so when we have the triple bond here at the very end, where the only other thing bound onto that is that H there, we call it a terminal alkyne. And when it's within right here, so it's bound to carbons on both sides, we call that an internal alkyne. And so these are butynes, so you can have one butyne, so we're starting the counting from this carbon, and over here we have the 2-butyne, and so we're starting from, I guess, either one of these end carbons would be correct. All right, so some physical properties of these. So generally the alkynes have slightly higher boiling points than the corresponding alkanes and alkenes. So for instance, if we have butane here, this has a boiling point of 0 degrees Celsius. The alkene has a boiling point of 6 degrees. Then the 1-butyne and 2-butyne have 8.1 and 27 degrees Celsius respectively. So we can see the physical properties of the melting points and boiling points here. The melting points don't really follow a great trend, but we can see with the boiling points that, again, sort of the more carbons we are adding on here, the higher the boiling point in general. And we see that, for instance, having a terminal alkyne is going to have a lower boiling point than having an internal alkyne here, sort of in general here. And so that sort of follows that trend for the boiling point at least, where the melting point doesn't have nearly as good of a trend for that. One other thing that's important here for our alkynes is that this gives off more heat per mole here. So we see that this has the negative 442 kilojoules per mole for the acetylene here, or the ethyne, whereas the ethene is only negative 352, and then the ethane is negative 312. And so that's why the acetylene is really good for welding here. And there are a few things that you have to do, in the tank for, sort of storing the ethine, but I won't get into that. So the point here is that we can give off more heat per mole with the ethine, and so that's what makes it better than, say, ethene or ethane for using these acetylene torches. And so this is just a formula here. I didn't really know what video to put it in, but since we've now sort of covered all of the alkanes, alkenes, and alkynes, or at least we're currently covering the alkynes, this is just a formula you can use for combustion reactions. So for finding out what coefficients you want to put in front of our combustion reactions. And so we see that the O2 is kind of the most complex one here, but this X comes from the number of carbons, and this Y comes from the number of hydrogens here, and then the M is something we can get from putting it in front of our hydrocarbon there. And so the M is probably something that you will increment if you put your numbers for the number of carbons, number of hydrogens into this, and you end up getting something that's a fraction. Usually that will end up being for our O2 here. Then you could increment the M up from 1 to 2, then put the 2 in front of each of these things, and you will end up, and if you then don't have any fractions as coefficients, then you know that you have gotten a good balanced chemical equation for this. But anyway, like I said, I didn't know where to put this in another video. So yeah, if that's something that you are interested in, then you can use that formula there. All right, so something that's important here about our triple bonds. So we've looked at these two things in previous videos for the alkanes and alkenes. So the alkanes, we have the sp3 hybrid. The alkenes is sp2, and this has a 25% S character. So if we, took one S and three P's here, so took 1s divided by the 1s plus 3p, that's 1/4, 25%. So it's 25% S character. And this has a pKa of 50, Where this we have a 33.3% S character and has a pKa of 44, so still a really, really weak acid, but it's still better than the alkane. Then we get to the 50% S character on our alkene, or alkynes rather, and we have pKa of 25, which again is not, a great acid, but we can see that it's considerably better than these other two things at being an acid, and so it actually becomes somewhat possible to deprotonate these things and use them as bases and nucleophiles. And so if we have our 1-butyne right here, we have a pKa that's going to be roughly 25. It's going to be a little bit different than our like acetylene because we have these here, but it'll be in the ballpark of 25. We can put this amide in here, which so the ammonia has a pKa of 37, so this is going to be an even stronger base than this will be, and so we can actually deprotonate that and turn this into a base and a nucleophile here. So these amides are extremely strong bases, and so these can be sort of hard to form. And in fact, you end up needing some pretty harsh conditions for this because, like I said, even though this is a better acid than, say, the alkene or the alkane here, it's still not a very good acid, and so you need something that's an extremely strong base in order to deprotonate it. And so using this, we can start synthesizing some alkynes from these acetylides. So this species right here is called an acetylide, sort of the base form of these things. And so we can do alkylation with these acetylide ions, so just adding them onto other like alkanes essentially. And so we can do this, so an acetylide ion, like I said, is a strong base and a powerful nucleophile that can undergo SN2 reactions, but it can also undergo E2 reactions, so like if the substrate has more bulky groups on it. And so this is done this way, so we have our acetylide right here. This will come bind onto there in SN2 reaction. The leaving group will leave, and so we are adding this R prime group onto it here. And so this would be sort of uh, a example of that. So we have our acetylide right here. This will come, it will bind onto this substrate here. The bromine will leave, and so we end up putting this ethyl group onto it like this. And so we're just essentially adding sort of these other like alkyl groups onto here. We're not, in the next video is when I'll get more into actually sort of the formation and reactions of these triple bonds. Here we're just talking about if we already have something with this triple bond on it, these are reactions we can do to sort of add other sort of substituents onto it. So here is an example where we have the E2, so we have these two more bulky groups onto this this electrophilic carbon right there. So we're going to take a hydrogen off of here. The electrons go down onto there. This will leave like that. And so we are forming this double bond right here and protonating this butyne right here. And so you're going to especially get these sort of side reactions like this because this these alkylide ions here, or these acetylide ions right here, are such strong bases because they're such their conjugate acid is so weak that these are just going to start reacting really fast with pretty much everything around it. And so you need a fairly unhindered electrophile or substrate there in order to get the get that alkyne or that acetylide ion to bond to the carbon there. So we can also add these onto carbonyl groups. So that's just the sort of basic reaction here. We have the nucleophile come in. It'll go after the partial positive carbon. The electrons from that double bond go onto that oxygen there so that we end up with this oxide ion here. So this will come, it can take a hydrogen off of the solvent there. So the electrons move there, and so we then protonate this, and we end up with this hydroxide here. And so we see we can do this with our acetylide ions. So we can do this onto a carbon like this that just has two hydrogens bound to it. So this formaldehyde here, so we can have that come in. These go there, and so we end up with this oxide group here that can deprotonate some of the solvent, and so we end up with an alcohol here. We can also do this on something that has these two R groups onto it, so we can end up with a tertiary alcohol right here. You could do it with a secondary as well, but we can see how the redundancies would go there. And so we have this here, so we have our acetylide ion, so this will come, it will attack that carbon right there. These electrons move onto that oxygen. We can then deprotonate or add this acid here to protonate this, and so we end up with this alcohol here. And so this happens to be a 3' or a tertiary alcohol that we've now added this triple bond carbon onto it. All right, so we can also synthesize the alkynes from elimination reactions. There are two elimination reactions. So the first is on the alkyl halide, and then we can do it on a vinyl halide. So the first step is doing it on this alkyl halide so that we form this vinyl halide. Then the second step is doing it on the vinyl halide, so pulling this hydrogen off and having this leave as the leaving group, and so we end up with our alkyne right here. And we see we can do this with the vicinal dihalides, so the halides are on neighboring carbons, but we can also do it on a geminal halide, so that the halides are on the same carbon here. And in both cases, we can end up with these alkynes like this. And we see that this first step is going to be fast, so this can happen fairly fast. Then the second step is going to be slow. And so we're going to need some pretty harsh conditions to do that second step. So like I said, there are two elimination reactions going on here. The first on the alkyl halide to get the vinyl halide, so forming that double bond. Then the second step is has to use these extremely basic conditions with really high temperatures. And so we can use the fused or molten potassium hydroxide, which is at 200 degrees Celsius, or we can use this amide at 150 degrees Celsius. And so at such high temperatures with such strong bases, this will encourage side reactions and rearrangements, so we end up getting pretty low yields because you're going to get a bunch of other sort of products from these side reactions that are forming. And so the potassium hydroxide at 200 degrees Celsius is best for these internal alkynes, where the amide at 150 degrees Celsius is better for these terminal alkynes. And so we can see that here. So we have this 2,3-dibromopentane right here. We do this with the potassium hydroxide at 200 degrees, and we are getting this 2-pentyne. And so that's about 45% right there, so that's a fairly low yield. Then we have this geminal dihalide here, so this 1,1-dichloropentane. We're using this amide right here. This would actually be at 150 degrees right here, so that should actually be our 150 degrees Celsius right there. Then the second step, we add this water right here, and so we end up with this terminal alkyne right here, such as the 1-pentyne. So that's a 55% yield right there. But anyway, those are sort of the ways that we can form the alkynes. In the next video, I'm going to talk about reactions of the alkynes, so actually using the pi bonds in these triple bonds right here to actually do reactions. And so again, they're going to be very similar to what we already saw with the double bonds in the alkene videos, so I'm not going to spend as much time on it. I can probably get through it in one video. But anyway, this was what I wanted to talk about in this video. I hope you found this helpful, and I will see you in the next one.